And okay, great. So thanks everyone for coming to joining my talk. My name is Jiangwei. Today I'm here to present our paper PG2S plus stat distance construction using popularity, gap, and machine learning. This work was done when I was a postdoc in National University of Singapore under the supervision of Professor YC Tay. So currently I'm working for Agoda. Caches are designed to store objects to accelerate future accesses to that data. So if a request object is already in the cache, and the request can be served much faster. Now, caching is widely used in content delivery networks, video on demand, etc., and much effort has been spent on caching optimizations. An efficient caching strategy could improve the system performances dramatically, and one of the common measuring metric is cache miss. A cache miss could occur if an object is requested and is not in the cache. This can happen if the object was never stored in the cache, or it was stored in the cache but subsequently replaced by other objects due to the size of the cache. The plot here shows an example of a miss ratio curve, where the y-axis is the cache miss or the probability of a reference resulting in a cache miss. The x-axis is the cache size, or we call it memory size. The higher the miss ratio, the worse the performance of the system. So except for anomalous cases, the miss ratio curve usually decreases as the cache sizes increases. Under the practical, replacement policies. So MRCs can be used to estimate the amount of data that's being used by a workload. They are not only useful for predicting cache performances for various cache sizes, but also helpful for automating cache management to balance the latency and the storage cost. For example, for VOD services, they might need to store video contents on hierarchical structures. For example, the first layer will be SSDs, the second layer will be hard disks. To effectively balance and determine the size of SSDs and hard disks and HDDs, we need MRC for this case. There are many cache replacement policies, and one of the most common used cache replacement policies is LRU. And in this paper, we only consider LRU caches, least recent used cache. With LRU, the miss ratio curve, the miss ratio for memory size m is equals to the fractions of references with stat distance greater than m. So as long as we can calculate the stat distances, we can calculate the MRC. Now here, the stat distance is defined as a number of distinct objects accessed between the current and the previous reference to that object. Besides the gap stat distances, we have gap distances as well, and a gap distance is a number of references between the two consecutive references to the same object. Here is a demonstration. The plot below is a demonstration of the gap distances and the stat distances. The first row represents the references. Here we have 13 references. And the second row represents the elements or the objects being referenced. For example, the fifth reference is requesting accessing the element C. And the third row represents the gap distances. For example, for the fifth reference again, the gap distance is 1. It's because between the last reference of C element is R3, there's only one element in between. So that's 1. And the last row is the stat distances. Let's take R6, for example. The sixth reference, for example, is A, and the last reference to A is R1. And in between, we have 4 references. So the gap distance is 4. However, we only have 3 distinct elements, which is B, C, D. So the stat distance is 3. To calculate the stat distances to construct the MRCs, we can roughly summarize them into two categories. One is step distance-based MRC construction. Another type is gap distance-based MRC construction. For step distance-based MRC constructions, the exact calculation of a step distance, the most efficient algorithm now is ON log m time and OM spaces, where m here is the number of distinct objects, where m is the sequence length. Apart from the exact calculation, we have sampling algorithms to make it faster. For example, step cache, HRS, and SHOTs, they are all sampling algorithms which samples the use sampling techniques to construct the MRCs. Moreover, we have RTH to CDH and a stack which they construct MRCs based on the gap distances. However, in a sequence of references, apart from gap distances and step distances, we have popularity. How frequent a reference how frequent an object get references, and this motivates our work. So in the next few slides, I'm going to share how to use popularity and gap distance to approximate step distances under the assumption of independent reference model. Means that we assume each reference are independently requested. Now, given a reference string R, which have many references, the gap distribution is defined as the fraction of references with gap distance d. And similarly, we can define the step distribution as the fraction of references with step distance d. And last but not the least, we can define the popularity distribution, which defined as the fraction of references with a specific popularity x. By having popularity and gap distances, PG2S theorem tells us that we can derive this step distance from popularity and gap distances. So in this presentation, I'm going to omit all the details of the proofs, so interested audience can read our paper for the sake of simplicity of this presentation. However, the idea of the proving of this theorem is very simple. If we look at given a gap distance of a specific reference request, we can calculate the probability of each distinct object that appearing in these such long gap distances sequences. However, bear in mind that it's possible that we can have two references which have the same gap distance and the same popularity, but different step distances. Here, the two references below give us an example where two references have same popularity and a gap distribution, but different step distance step distributions. In the example here, it all has 6 references, and the elements being requested is the same, A, B, C, D, where D is referenced by 2 times and C is referenced by 2 times. So the popularity distribution is the same. And if you look at the gap distance, for D, the gap distance is always 0. And for C, for both cases, is 2. However, the step distances for these 2 references are different. Besides the PG2S theorem we see previously, there is a P2G theorem as well. And this theorem tells us that we can simply derive gap distribution from popularity distribution, again, assuming our independent reference model. Now we can move furthermore, and this P2EG theorem tells us that we can in fact derive the estimated gap distances from purely popularity of a specific reference, assuming the RNN. And if we link these theorems together, we can simply derive that we can simply approximate step distances purely based on popularity. Now, before I'm moving further to demonstrate, moving further to PG2S plus, I'm going to share with you some of the results that we can derive from PG2S. So this is an example where we use PG2S to predict the MRCs on a independent reference model under the assumption of independent reference model. And we achieve these independent references by shuffling empirical data. So this, we took the trace from the empirical data and shuffle it randomly to form the independent reference traces. And we can see that the plot on the left plots the gap distributions that predicted by P2G versus the ground truth, and the right plot plots the MRCs constructed by the PG2S and the ground truth. We can see that both gap distribution and MRCs have a very similar performances, and our model is accurate in make the predictions on the IRM. However, for non-IRM cases, that's not true. If we look at the same empirical data without shuffling the trace, we'll find out that our predicted gap distribution is higher than the empirical data, and again, the predicted MRCs is higher than the empirical MRC. The predictions for PG2S and P2G in this scenario on the non-IRM cases are not accurate. The question is, how should we move from IRM to non-IRM? Now, there could be many possible solutions and many possible proposals, and one could just propose different solutions for different specific correlations. Say, for example, we can make assumptions of the arrivals of the sequences. For example, we can make assume that the references is self-similar. So similarly, we can prove a theorem called PG2S theorem for self-similar arrival, P2G theorem for self-similar arrival, P2EG theorem for self-similar arrival, and so on and so forth. But the problem is that this is kind of lacks of generality and it's not scalable, because we could have so many or possibly infinite such correlations among the arrivals. For example, next day somebody going to took a social network arrival traces or says that, hey, I'm going to propose a solution specific for social network arrival. Then the question is, should we again propose PG2S theorem for social net arrival, P2G theorem for social net arrival? And in our case, we feel that this is not exactly unscalable. So instead, we try to learn the discrepancies and make predictions based on the discrepancies we learned in the past. Now, if we revisit this non-IRM predictions using PG2S, now we find out that the gap distribution seems like has some correlation with MRCs. If we look at the gap distributions predicted, seems like always higher than the ground truth, and similarly, the MRCs is kind of higher than the ground truth. Now in both cases, they have these kind of discrepancies, but does the discrepancies in the gap distribution implies the MRC discrepancies? And this is what we are trying to capture, and hence we proposed PG2S plus. So in PG2S plus, we utilize these kind of discrepancies. PG2S plus consists of 4 components: PG2S, P2EG, P2G, and machine learning models. So machine learning models takes several inputs: the trace length, the estimated stat distance, estimated gap distribution, the real gap distribution, the estimated popularity, and so on and so forth. So the intuition here, there is a difference between the ground truth gap distance and the estimated gap distance, and the differences between the ground truth gap ratio and the estimated gap ratio, and so on and so forth. So that there could be an intrinsic relationship between the discrepancies things here and the predicted statistics and the real statistics. So we use an MLM model to learn and predict the distance distances based on the deltas we learn here. So in this case, we thus view MLM just as a computing function f which computes the deltas. So, and in our case, PG2S plus is not specific to any LM model. In our paper, we present results from two representative deep learning neural networks. One is called CNN, and in this presentation, I'm going to demonstrate how CNN performs in our scenario. So in the next few slides, I'm going to present the experiment results, and the experiment uses traces from two places. One is iQIYI, where iQIYI is one of the largest video sites in the world, and we extracted 1 hour access log from one of the servers from iQIYI. And each machine has about 1 million references and 58,000 distinct references. Moreover, we took traces from Microsoft Research Cambridge, and the traces are 1 week block IO traces from those enterprise servers, where there are 3 servers we extracted traces. We extracted media servers, which is 1.2 million references and 0.1 million of them are distinct. For research servers, there's 1.4 million references and 46,000 of them are distinct. And for source control servers, we have 1.5 million references and 80,000 of them are distinct. In order to train the model, we partition the traces into different subtraces, and each subtraces is partitioned to X sequential subtraces of equal size, where X ranges from 50 to 400, and for each trace, we use 90% of them to train the machine learning model, and the rest of 10% are used to evaluate the performances. And for evaluation methodology, we take 3 different approaches. The first one is we call intra-workload validation, where we always use the subtraces from the same data set for modeling, for model training, and the testing. So for intra-workload validation, it's kind of to simulate the scenario where the model is only used for single workload. For inter-workload validation, we use mixed subtraces from mixed data sets for model training and validate performances for the performance on these mixed data set subtraces. For inter-workload validation, this is to simulate the scenario of applying a model of training of mixed types of workloads and make predictions. The last type of validation is we call tele-workload validation. And this is more exciting because we validate the performances of subtraces where from new data sets, which is never used in the training. And for these tele-workload validations, the model has 0 prior knowledge of the data set we are going to be tested. And this is more challenging and probably has a wide application of the use cases. So before we moving on, compare PG2S plus against other algorithms, let's just first compare PG2S against PG2S plus. So here we present the results from research machines from Microsoft Research. And for more experiment results about the data sets, please check our paper. So we can see that, and for the PG2S plus of intra-workload training, the data set was training on the research data sets and for inter-workload validation, the data set, the training was done on mixed subtraces from research and iQIYI. For tele-workload validation, we trained on media server, source control server, and iQIYI traces. So we didn't use any subtraces from research server to train the model. As we can see here, for PG2S, PG2S performs well for trace 3, subtrace 3, but badly for trace 1, and okay for trace 2. But however, for PG2S plus, we can find out for all the 3 scenarios here, we make decent performance. We have a decent performances for all three scenarios and the predictions. Besides comparing PG2S Plus against PG2S, we compare PG2S Plus to other sampling, to other state-of-the-art algorithms. There are two sampling algorithms and two analytic models. So HRS is a history preserved representative sampling. The references are partitioned into sampling and hibernating intervals. So HRS only samples references to objects that are previously referenced in the sampling intervals. Now, SHATS is a hash-based sampling technique for stat distance analysis. It allows fixed rate sampling and fixed size sampling. In our case, we use fixed rate sampling. So stat distance estimates the stat stack estimates the stat distance based on gap distance and a forward gap distance. Here, the forward gap distance are defined as the gap distance as the number of requests until the next references of the same object. And RTH to CTH approximates the stat distribution based on gap distributions. Here, we present the experiment results for some subtraces against other algorithms. As we can see from here, it looks like RTH to CTH is always the upper bound of the ground truth, and a stat stack, again using the gap distribution, is a lower bound of the ground truth. And we suspect this is due to the low popularity of the traces, where as RTH to CTH requires high popularity to work. At the same time, we find out that the sampling-based algorithms has a closer performance to the ground truth. And again, PG2S is always the best among these algorithms. For more experiments on more traces, please check out our paper. Apart from experimentation on empirical traces, we compare the performance against other algorithms on traces generated by benchmark tools. So we ran 13 real programs using spec CPU 2006 and collect the traces from these 13 real programs, and then we train the models using 10 programs and evaluate the performances using the last 3 programs for testing. So in this case, this is another tally workload validation. Again, for the traces on the spec CPU 2006, we find out that on RDH and a CDH, RDH to CDH and a stat, again, is still the upper bound of the ground truth, and a stat is still the lower bound of the ground truth. And sampling algorithms are in the middle tier of the performances, and PG2S, again, is the best among the algorithms. And this concludes my presentation. So in summary, in this paper, we present PG2S Plus, a framework for predicting cache misses that is the first to combine reference popularity and gap distribution. A PG2S Plus correctly computes MRC on the IRM, and for non-IRM traces. Independent of the machine learning models, PG2S Plus is more accurate than other algorithms. And we formally establish the relationship between frequency and recency through the P2G to us theorem, means that by simply using popularity, we can construct the stat distance. And thanks for the time of joining my talk, and we will open for questions.
Thank you very much. You can stop the screen sharing. Thank you. Now we go to the last talk that is recorded and is scaling page rank to 100 billion pages by Sturgeon of Google, from Google.
Please stop share screen, thanks.